Okay, so we've learned about Bernoulli's equation. We have used Bernoulli's to measure the airspeed of an airplane, for example, calculate how long it takes to empty a coffee maker cone, or empty a pool. And now we're going to use it to um, estimate the velocity of air over a wing. So the first thing we're going to do, first thing we're going to do is we're going to estimate the streamlines that go over a wing, and then starting at one end, starting with one ending in the stagnation point A, we're going to let's assume we've put pressure taps in that allow us to measure the pressure along this wing, and these pressures are given by these pressures here. And given these pressures, calculate the velocities at A, B, C, and D. So first thing we do is we have to estimate the streamline. So we know there's going to be a stagnation point, and what's actually really interesting is that you'd think the streamline that comes straight in would hit that stagnation point, but it's not actually. It's a streamline that comes a little bit below, comes up to hit that stagnation point. And then I'll do a streamline below, comes down like this, and then off, and then pause the video and you draw a couple streamlines above this. Okay, I'm going to assume you paused it. I'm going to draw up, over, and down. Draw some more streamlines, and it looks beautiful. Great. So now that we've estimated our streamlines, we want to actually look at a streamline that starts essentially at the stagnation point. So our velocity is basically zero, and then comes around this surface like this and comes off like that. So that's going to be our streamline, and we're relating pressures and velocities. So we know since things are moving, we're going to have to use Bernoulli's. So let's write out our Bernoulli's equation. P1 plus 1/2 v squared times rho plus g z1 is equal to p2 1/2 v squared, that's v1 squared, v2 squared times rho plus g z2. We're going to have to write down some assumptions now, again, to help ourselves, our future selves, our future coworkers, and the graders. We're going to neglect height because it's a gas. We're going to assume inviscid, and we're going to assume rho is equal to a constant and steady state. Inviscid in this case isn't the worst assumption. There is a viscous layer we'll talk about at the very end of the semester, a viscous layer very close to the wing where a lot of the viscous effects occur, but just a little bit away from that layer, and that layer can be as thin as like a piece of paper. Just a little bit away from that, viscous effects actually are relatively unimportant. So neglecting the height is also a good assumption in this case. So since we're neglecting height, we can neglect the z's. So let's label these A, B, C, D. So A is going to be equal to 0 due to A. Now we got to ask what we know. We know P1. We know P2 because we're going from either from A to B, A to C, or A to D. So we always know pressures, which is great. We know V1 because V1 is essentially 0, close enough to 0. That is the stagnation point. Notice we can't actually use the stagnation point because that actually goes to 0, and so that fluid never leaves that point. But if we go near it, the fluid will come around and go past these other points. So since we know V1 is equal to 0, that leaves only V2 to be solved for. And if we take equation 1 to equation 2, where we solve V2 is equal to the square root of 2 times P1 minus P2 all over rho. Great. And then we just apply it. So for A, for example, we get 0 meters per second. Because P1 is equal to P2, because, yeah, that's P1 minus P2 is 0. B, we get our velocity equals 75 meters per second. And I'll let you guys do the rest of these. Okay. So, bonus, let's draw the streamlines for a stalled wing. Now, a stalled wing, we'll talk about this, means that the flow is separated from the wing. So, typically you'll still have a nice streamline coming up and hitting, stagnating at the beginning. One thing I didn't mention is that in a wing you typically get another streamline that comes off the back that's stagnating, and what stalling means is that that streamline that stagnates at the very tip of the wing, the sharp point there, typically moves up somewhere up right around here, or somewhere in this region, and you get a streamline that goes like that. So now if you were to draw a streamline, you go up like this. This one still comes down. And now you have a low pressure region in here. Oops, that doesn't look very good. And so you get some recirculation in this region. But the most important thing you have is that normally you have, if you look up here at these pressures, PC is quite low, 101.3 kilopascals. PB is 99.8 kilopascals. You have very low pressure in this region here, which is where a lot of the lift, even here you have a low pressure. All the lift is generated by having a high pressure on the bottom and a low pressure on the top. By the way, what that high pressure on the bottom does is it pushes air down, and the low pressure pulls air down. So there's lots of ways of thinking about why an airplane generates lift. You could say it's because it forces air down, but you can't force air down without having pressure differences. So the two are synonymous. The important part, though, is normally we have low pressure here at the top, but if we have a stagnation point here, that means we're going to have a P high here, and our flow is going to be much slower in the region around the P high. And so we're going to have a region of high pressure on top, a region of high pressure on the bottom, and our wing is going to cease to generate a lot of lift, which is why stalling is so devastating. Incidentally, you'll notice that a lot of planes have little tabs sticking off the end, and those are stall sensors, and what they sense is they sense the air coming up. Usually it's turbulent, so it makes them flap up and down, but they sense the air coming up, because normally when a wing is working correctly, the air is coming down like this, but if it starts coming up, they know that the wing has stalled or is going to stall soon. A well-designed wing doesn't stall all at once. It stalls in a few spots, and then the pilot has plenty of warning. So, cool. All right, next problem. Flow measurement in pipes. So we're gonna take a pipe. We're going to put an orifice in it, which is just a plate with a hole in it, and then we're going to take a tube that connects before and after the orifice, and put a differential pressure sensor across that tube, so that we know the pressure on this side versus this side, the difference in pressure. So, given P1 and P2, can we estimate V average? So we already have experience with airplanes, so we can guess that if we have two velocity measurements, we can, in an understanding of the fluid that we're using, we should be able to estimate V average. So we're relating pressures, velocities. Which model should we use? Well, there's really only one at this point, but Bernoulli's is a great model if we know we don't have to deal with viscous effects to relate pressures and velocities and heights. So the first thing we're going to do is we're going to draw streamlines for fluids going through the orifice. So we're going to go here. Streamline comes up, circuits. Remember what we said about fluids going around a 90-degree corner? Can't do it. Just like you, just like a car. Well, every car except for Batman's car. This is what made Batman's car so brilliant, right? That grappling hook that let it hook onto light poles at the corner so it could go around a 90-degree bend at like 60 miles an hour. It's amazing. But fluid doesn't have that. So it misses the bend and keeps going, but produces a recirculating region here. It does the same thing on the bottom. Misses this bend and keeps going, produces a recirculating region here. And we can see that the streamlines, the rest of the streamlines go through like that. And depending on the Reynolds number, depending on the speed of the flow, this can be this neat. It can be quite a bit more complicated. Let's use a different color for the complicated flow. You could have large regions of turbulent rotational flow afterwards, or you can have these neat recirculation regions and the flow quickly reattaches to the wall. It really depends on the speed that the fluid is going. But let's draw. Let's write out our model. So our model, we're going to do equation 1 is pressure divided by density. P1 is equal to or plus V1 squared divided by 2 plus GZ is equal to Z1 is equal to P2 plus V2 squared divided by 2 plus Z2. And we got to draw a streamline for Bernoulli's. It's like the free body diagram for Bernoulli's equation. You just got to do it. So let's do it. I'm going to pick here. And go all the way in. We're going to cross the differential pressure sensor and go here. Great. So now, just like with the differential pressure sensor, we're going to assume not orifice, because that's where we're using that term. Pressure in holes equals bulk, right? So we're going to assume that the pressure here is relatively equal with the whole center area. And the reason we can assume that is if there was a pressure gradient in this direction, again, there would be fluid motion in the direction of the pressure gradient. There has to be, or there has to be some acceleration of the fluid. So either the fluid has to be going around a corner or something like that. And since there's not, we can assume that the pressure is pretty much equal across this whole entire cross section. And the same is true here. We have some kind of average pressure that exists here. So P is equal across entire cross section. Great. We're also going to assume inviscid. So we're going to call both of these A. We're going to call B inviscid, C density is equal to a constant, and D steady. Awesome. So we're basically at the same height, right? We got to label these 1 and 2. We're basically at the same height. So Z1 is equal to 0. Z2 is equal to 0. Sorry. And so now we're left with how many unknowns? Well, we know P1. Oops, we messed up here. It's P2 divided by rho. We know P1 minus P2 divided by rho, we know that from our differential pressure sensor. So 1 to 2. We got that. And that's going to be equal to V2 squared over 2 minus V1 squared over 2. We don't know either one of those. So again, we have two unknowns in our equation, so we're going to have to get a second equation. So let's do that. 3, we're going to do V1 A1 is equal to V2 A2. So velocity times area is equal to velocity times area. This is our conservation of mass equation for an incompressible fluid. If our fluid is incompressible, then we could compress the area, keep the velocity the same, and just increase the density. But it's water, or we're assuming some kind of liquid, so we can't do that here. By the way, I should mention, there are streamlines, by the way, that come right along this corner and go right up like this. We didn't draw them in. All right, so we're going to solve for V2 in this case. 3 to 4. V2 is equal to V1 A1 over A2. Excellent. We're going to plug in equation 1 into equation 4 into equation 1. So 4 plus 1 gives us 5. Sorry, not equation 1, equation 2. Gives us equation 5. And so we're going to have P1 minus P2 times over rho times 2 is equal to V1 squared, V1 squared A1 squared over A2 squared minus V1 squared. Cool, which we can simplify a little bit farther by saying V1 squared times A1 over A2 squared minus 1. Great. And so we're going to go from equation 5 to equation 6, and we're going to say that V1, we're going to do some algebra here, V1 is equal to the square root of 2 P1 minus P2 over rho times the inverse of this here, which is 1 over A1 over A2 squared minus 1. Great. So this requires us to know A1 over A2. Now, if you're clever, I haven't specified A2 at all, right? Or A1. We know A1 is equal to the diameter of the pipe, but what is A2? So we still are kind of confused about what A2 is. Well, it turns out for an orifice, this is actually a well-known relationship. So we know that A2 over A1 for a given Reynolds number, this is equal, A1 over A2 is equal to a function of the Reynolds number. So we can pretty easily, and the Reynolds number, by the way, is equal to rho VD over mu. So we can't solve for this directly because it's an implicit equation. Velocity appears multiple places. But we can implicitly solve this with a computer very easily. So this actually turns out to be a decent way to solve this problem. But we have some questions for you. Is this rotational or turbulent flow? So if we scroll up here and we look at this beautiful drawing, I'm going to let you fill that in. Is this rotational or turbulent? The answer is yes. Possibly highly. And what would be the sources of error here? Well, sources of error are not knowing A1 over A2, right? So A1 over A2, if you don't know it for the particular geometry, or you have an error in your geometry, that will cause errors in your equation. You also might not know the density of the fluid very well. If you don't know the density of the fluid very well, that directly affects your results. Another source of error is viscous losses, right? So this equation predicts the velocity as a function of pressure and area. But like we talked about, Bernoulli's is an energy equation. Pressure energy plus velocity energy plus height, potential energy goes into pressure, velocity, and height. But what if some of it also goes into losses? Then there's going to be some error, some error that our V2 is going to be smaller than we would expect it to be, and as a result, our V1 is going to our pressure 2 is going to be smaller than we expect it to be also, and our V1 is going to have some error in it. So the viscous effects would cause error. That's an error in our model. There's also the fact, like I said, that we don't really know A2, and that requires its own model, which could require could add additional errors into the system. So how can we mitigate these sources? Well, the answer is spend more money. Almost always the answer, isn't it? We can use a better geometry. So we can construct what we call a Venturi Meter, which has a relatively fast constriction and then a slow expansion afterwards. If we draw the streamlines for this, it's specifically created so that the viscous, we don't get separation, right? We don't have any 90-degree bends that the flow has to go around, so it doesn't separate, and it doesn't create these vortices and these eddies that really generate a lot of viscous losses. So it's one, it's more efficient. Two, we know the different areas. We know the area here. I would call this, whoops. So we could tap it here, put a pressure tap here, and put a pressure tap here. We know A2 and we know A1 very well because they're constrained by the geometries of the system. The reason why we can't actually use the diameter of our orifice here, by the way, is because the water tends to overshoot the orifice and actually create a smaller diameter than the orifice requires. Again, water can't go around a 90-degree bend. So it overshoots it, and the area here is actually smaller than the area you might expect. So yeah, but these are expensive because creating tubes with a variable cross-section is expensive. What's cheap is to take a tube and just weld in a plate with a hole in it, and then you're done. Well, weld in a plate and a hole, drill a couple holes and weld a tube in, and then you're done. So, yep.